Hi, I'm Dennis, and today I'm going to talk about our work at most Hexa meshes. It was developed with Hendrik Lensch in Tübingen and in collaboration with Tarini. I'm currently in a research position at the TU Dortmund in the geometry group of Mario Bosch. So let's start with a bit of background on geometry representations. In the most simplest form, we have implicit representations like point clouds from 3D scans. These are, however, rarely suitable for downstream applications. Therefore, we can use common surface reconstruction techniques to generate closed surfaces, usually expressed as simple triangle meshes or higher quality quad meshes. Now that we have a surface, we can go one step further and also define meshes that actually transcend the volume of the object and partition the input domain into small, feasible primitives, in this first example, tetrahedra. Here we have an analogy to surface meshes with triangles and quads, and in volumes we have tetrahedra and hexahedra. There are methods to generate hex meshes, which can start from a surface or tetrahedral mesh, but they usually also require additional input which is far from trivial to generate, ranging from mappings and parameterizations over frame fields, singularity graphs, to manual segmentations of the input. What I'm going to explain today is a method also focused on the generation of hex meshes, but starting from much simpler input, which does not require additional data. A point cloud or surface is already sufficient. Now a quick overview on the classification of current state-of-the-art hex meshing procedures. First, we have all hex methods, which are great, because if you have only one type of primitive, that is very convenient for computation and storage. But then they are difficult to construct as they require complex input, sometimes even created manually. And you always have to balance element quality against input fidelity. Quality is herein usually measured as the skewedness of individual primitives, expressed as the minimum scaled Jacobian. With the hard constraint on hex only, if the input is bad, they sometimes fail and produce inverted elements, which makes the result unusable for further computations. Then we have an alternative called hex dominant. They have an easier life at producing their output because they relax the definition of a hexamesh. And they do so by allowing for elements that are not hexahedra. This is great for them because robust automatic production of hexameshes can really use that help. But on the other hand, it considerably complicates the usability of the output. The visualization here shows elements simpler than hexahedra in yellow, and the more complex arbitrary polyhedra are shown in red. Now, we also propose to relax the definition of hexameshes, but to a lesser extent. That is, we target a more bland generalization of hexameshes, which we call at most hexa meshes. They are more general than pure hexa, but less general than hex dominant. We allow for occasional elements that are not hexahedra, but crucially, we only want cells that are simpler than hexahedra, unlike the general hex-dominant case. And we still disallow any cell that is more complex than a hexahedron. Our observation is that this generalization is still very effective at easing the task of hexameshing, as I'm about to exemplify with our construction algorithm. At the same time, we can argue that our more parsimonious generalization of hexameshes has a lesser impact on downstream applications. Now a little introduction on what at most hexa actually means. Therefore, we can have a look on the primitives that we use in our mesh, where the base case is a hexahedron. We encode this as a tuple of 8 integers indexing the 8 vertices, enumerated here with letters from A to H. Smaller primitives are now constructed by collapsing edges of the hexahedron. Here, for example, one collapsed edge creates a hex prism. The collapsed edge is encoded simply by doubling the vertex index. By collapsing more edges, we can construct more primitive types, all encodable as hexahedra. Therefore, the resulting mesh files are easily suitable for all Hex processing pipelines. Now let's have a look on how to construct a mesh from these building blocks. The premise is to use a surface hull or point cloud as input and with some magic generate a volume mesh. Obviously, there are some interesting steps in this pipeline, as I will show you in the following. The first one being a Lloyd relaxation. Therefore, we fill this volume with cells of a three-dimensional Voronoi diagram, which will eventually align to our input object. But therefore, first a quick intervention on the specialized type of Lloyd relaxation we use here. So in the most common scenario, Voronoi diagrams are usually defined using the L2 norm, which is simply the Euclidean distance between 2 points, where the level set of this function is a circle, at least 2 dimensions. As you all know, a Lloyd relaxation now repositions the sides of the diagram on the geometrical centers of the cells, and as the iteration continues, this converges on a centroidal Voronoi diagram where the centroids and sides eventually coincide. Now for our purpose we modify the distance function and use the L-infinity norm, which has a square-shaped level set. Now the relaxation also converges on square-shaped cells, or in 3D, hexahedral cells. We can now further extend each cell with its own orientation and give the cells a shape to which they can align to. In our procedure, this is obviously the input object, or with a little trick, also a point cloud. Therefore, point cloud samples actually participate in the Lloyd relaxation with their own Voronoi cells. However, their position is not updated and their cells are flattened and widened. Now the cells align accordingly to the input. The relaxation alone, however, does not guarantee for proper cell alignment. Therefore, we need additional regularization forces. These also apply during the relaxation phase and pull cells into a grid-like arrangement based on a special nearest neighborhood. Here we can now see the result after the constrained relaxation. And it looks like we're almost there, right? But these are still cells of a Voronoi diagram and far from hexahedral. These are still arbitrary complex polyhedra. So to generate the final mesh, we need to generate the geometry. Therefore, we replace each cell with a unit cube scaled to the volume of the cell and oriented accordingly. Vertices of these cubes can now be snap merged based on the distance and neighborhood relations. While this gives us the final geometry as this skeletal structure of edges, the missing link here to complete our pipeline is the topology extraction, to recover the Atmost Hexa constellations for our final mesh. So based on the edge structure, we are now searching for our Atmost Hexa primitives. This is basically a graph search based on faces within the edge complex. Therefore, we have defined a set of pretty straightforward state machine programs for the extraction. Here, for example, with a hexahedron. The third state is defined as 1 quad face, 0 triangles, and 4 open edges. The only transition we are allowed to do here is to add another quad face. This closes 1 open edge and adds 3 new ones. The next valid states both have 3 quads and either 6 or 8 open edges. After that, we again only have one possible option for the next step, which in the best case also allows to reach the final state with 6 quads and 0 open edges. And the cool thing here is that the last step is actually trivial, so if you make it to the penultimate step, we're already fine. If we can't reach this step, we have only wasted 3 steps on a failure, which is very little overhead compared to similar approaches, for example, based on tetrahedra instead of faces. We have defined these state machine programs for all primitive types and can start our graph search. The individual primitive types are independent of each other and the search can run in parallel, so that all primitive types are collected at the same time. If we now look at all the collected primitives, the histogram over the primitive counts does not at all reflect hex dominance, but only because we have way more primitives than we actually need. Therefore, we are now challenged with the assembly of our final mesh, and for that we can simply start with the collected hexahedra and look for suitable primitives to fill up the holes in this volume. Therefore, we can use this collection of primitives, which is sorted as in this diagram. First by primitive type and then primitive quality, shown here as the black curve. So it's basically a priority queue where, if possible, we use the best elements first. Now our assembled mesh looks like this. So we have basically filtered out the majority of non-hex elements and only used the best suitable ones to complete our mesh. From the 200,000 available elements, we have now used 9,500, where about 90% are hexahedral. So now we are back on track with the hex dominance. Now let's compare some results to state-of-the-art methods. Here I have listed some numbers of 3 example objects. The table gives the number of primitives and the time for the computation. But more importantly in percent, the number of hexahedral elements and the volume they occupy. And for quality, the minimum and average scale Jacobian. And as we can see, we can definitely compete with the state-of-the-art. However, I think these methods and numbers are a bit difficult to compare, as the different competing methods aim for different goals, and also often start from very complex input, sometimes even manually optimized. So I would rather focus on a qualitative comparison, here for example with 2 results from a hex dominant method and 2 all hex results on the right. We can see that the hex dominant competitor produces comparable results to ours, but obviously features these arbitrary polyhedra in red, and both examples on the right even feature inverted elements. So here I think we can see that we found a good middle ground with our special hex dominant meshes. For an outlook on future improvements, one thing could be to exclude outside cells early on. Currently, the Voronoi diagram and Lloyd relaxation is performed on the volume of a padded bounding box around the object. Close to the object's hull, we need cells on the inside and outside, but outside cells further away from the hull could be excluded in the computation to improve performance. Another point for improvement is the realization of the L-infinity relaxation. While L2 diagrams are easy to compute, L-infinity diagrams are not. Therefore, ours is currently only an approximation on a high-resolution volume grid. This could be replaced by actual L-infinity cells in a proper relaxation. In our paper, we've experimented with additional guiding structures, transcending the object so that cells can align to them. This is technically quite simple and I think has great potential to further improve the results. So to conclude what we've seen today. Our Atmos Hexa meshes can bridge the gap from point clouds to volume meshes without additional data or the necessity to pre-compute a surface. We saw that they can level with the state-of-the-art both in terms of primitive quality and quantity. But the potentially most valuable contribution here is the novel mesh class, which combines the benefits from hex-dominant and all hex meshing approaches, as our results can be encoded as normal hex meshes and used as such in downstream applications like Graphite or Hexalab. Our examples have been added to the Hexalab benchmark, although it was designed with pure hex meshes in mind. We didn't have to invent a new file format for our meshes, and we could reuse the standard ones intended for pure hexa meshes. And most visualization features, including the identification of irregular edges, work just fine. As another example, when it comes to the automated evaluation of shape quality, for example with the minimum scale Jacobian, our non-hexahedral elements are automatically considered to be minimal quality, which we think is appropriate. This reinforces our hopes that Atmos Hexa meshes can be employed by many downstream applications which expect pure hexa meshes as input with only minor modifications. More investigation is clearly needed to fully assess this, especially when finite element methods are involved. But it was encouraging to see that all visualization functions of HexaLab and a few functions of graphite worked straight out of the box as is when we used our bland generalization of pure Hexa meshes. And with this I conclude my presentation and thank you very much for the interest.